Okay, so I hope my screen is visible to you all. So let's start this session. So uh, welcome you all to the live interaction session of NPTEL. The course is Sustainable Power Generation System being taught by Professor Pankaj Kalita, and I am Rohit. I'll be taking this live interaction session as a teaching assistant. So teaching methodology remains same. I will first revisit whatever taught in revisit whatever is taught in the previous week lectures, and then after revisiting the concept, we can proceed to the solving the quiz question. After the quiz questions, we'll discuss some other topics, related topics, and if there is something uh, if there's something which you need to ask, which you want to raise your doubts or something, so please feel free to ask your questions in between by raising your hand or writing it on the chat box. Okay, so this is the global primary energy consumption by source. So actually, if you see this figure is actually representing contrasting detail about some of the how energy is being used throughout the globally and in India. So you will see some differences, some major differences. Like I want you guys to focus on this figure for 1 or 2 minutes so that you can see how world is using the primary energy and how India is using the primary energy. So there is a concept here like what is a primary energy and what is a secondary energy. So primary energy are those energy that are found in its natural form. So they can be harnessed directly from the nature in its form. But in secondary energy, we process those primary energy to convert it to some other form like electricity is a secondary energy. But similarly, okay. And heat is basically a primary energy, but it depends if it's originating from source like calorific value or something. It's a primary energy. Okay, we'll look at this figure. So did you observe any difference in between these two figures or something which you think is quite noticeable or can be looked into? So let's see if any one of you has raised something. Okay, so no problem. Uh, let me show them to you actually. So if you see this, okay, this is basically coal consumption. So the world, if you see the global coal consumption by 2022, the sector here covers only a fraction of what the India is consuming coal as a primary energy for producing. It can be anything for producing secondary energy or heat or anything, but uh, more than 50%, if you see more than 50% of India primary energy demand is basically fulfilled by the coal consumption. And then the second thing is that oil consumption. Okay, so almost if you see the oil consumption levels, those are very similar to Indian oil consumption levels are very much similar to whatever we see for this global oil consumption. But for coal, there are certain differences. Similarly, for hydro gas consumption, I think this is gas consumption. So yeah, similarly for gas consumption, because we don't have so much of gas power plants, and if you see the Western countries like Europe or UK, US, they have got quite a good amount of power plants as gas-based power plants. So yeah, so basically, and they use gas, natural gas, um, in a like big manner or something you can say, like even in this Russia war, Ukraine Russia war, they were very much dependent. The Europe itself is very much dependent on other like countries like Russia for their natural gas supply or consumption. So that is one of the major differences that we don't have here in India. But coal and natural gas are certainly two of the important things that we see a stark difference in what world is using and what India is using. Okay, but if you see both the figures, there are some similarities also. Like in the global primary energy demand and Indian primary energy consumption, both are being dominated by the fossil fuels. So we have the dominance of fossil fuel is still going on even after the push for renewables or push for solar energies being given by the governments, and more talks about these renewables are going on, but still these fossil fuels are the share of these fossil fuels are still intact if we see global or if we compare it with Indian primary energy consumption. But the problem uh, is actually not coal or not fossil fuel. The problem here is the share of renewables. So it's not a problem. It's actually we see that the share of renewables are actually increasing. But the term I was saying the problem. But you can see these are actually based on the capacity. But you see the generation graph, those renewables doesn't contribute a lot much to this whole energy mix actually. So that is one of the challenging aspect of having renewables. So they don't operate at all times, so there can be some if and buts also, some trade-offs also. So these things are there. And as of 2022, less than 3% of installed generation capacity in India come from biomass power, cogeneration, and waste to energy projects. Okay, so still we are having a lot of push for anaerobic digestion. We are having a push for using biofuels, but still, as of 2022, they contribute less than 3% in the total installed capacity of India. Okay. Now the question arises here is what is basically a biomass, okay, or biopower or bioenergy. So biomass is basically renewable organic material. So material made up of organic like carbon that comes from plants and animals. So it has to be has to come from plants and animals. But yeah, in case of municipal solid waste, if you remove the plastic fraction, it does have a good amount of biomass content in it. Like paper does come from plants, and then biomass contains stored chemical energy from the sun that is produced by plant through photosynthesis. Biomass can be burned directly to generate heat and convert to liquid and gaseous fuel through various processes. So yeah, we will look for these technology in upcoming slides. But yeah, we have well developed technologies that convert biomass to heat, like we have incineration to produce heat, and then we have pyrolysis to produce liquid, and then gasification or gasifiers to produce gaseous fuel. So yeah, we have a lot of work is going on, but still we can see a lot of improvements and in these products, and in future these products may contribute or will be contributing a lot to the energy mix also. In the process of photosynthesis, the plant convert radiant energy. So this is the reaction. It actually fixes the carbon dioxide in the atmosphere to some form like glucose, and then as a byproduct, oxygen is generated. Um, So if we see the average efficiency of conversion in solar energy to biomass energy, so plant basically has an efficiency of 0.5 to 1%. So this is very, very, very low efficiency. Like if they are consuming a lot of solar energy, then very few amount, like less than 1% is getting converted to biomass energy. Hello? Okay. So now you must have got a good idea about what constitute bioenergy. So that has some organic origin and derived from plant and animals. Okay. So there are some usable forms of bioenergy, like fuel wood is one of the major form. So most of our, if you see the biomass energy consumption in India, most of it in the terms of fuel wood only, because a lot of people in the rural or off location areas uses fuel wood as a fuel in their gas stoves for cooking and many things like heating purposes in winter. Biodiesel is one of the form of biomass. Biogas is there from anaerobic digestion. Fuel pellets and briquettes are also there. So where these fuel pellets and briquettes are actually used. So these are basically generally used in cement kilns or some like brick kilns. So they are basically mixed, used there to provide power like heat uh, to some usable forms that can be convert that can be used to carry on the processes like industrial process or something. So these are basically mixed with some fuel also sometimes. Bioethanol is there. Bioethanol is now a trending topic because we just want our because a lot of energy security of India is questionable when there is a lot of dependence on foreign countries for fuel. So yeah, we do have a lot of amount of biomass, and we just want to harness those biomass to generate ethanol. Okay. Another one is producer gas. Producer gas is basically produced from gasification of some biomass material. So these biomass material can be anything which is listed in the previous slides also. And when these producer gas basically has a good calorific value. So yeah, these can be utilized for generating power, generating heat. Similarly, charcoal is one of the form of biomass generally derived from partial combustion of coal. Now, if you introduce the biomass, like introduction of the biomass, so different biomass conversion routes to electricity are there. So these routes basically can be classified as a thermochemical conversion and biochemical conversion. And thermochemical conversion basically looks into converting those um, basically using those biomass to convert to various products like steam, gases, heat, oil, similarly using some thermal methods. That is a combination of thermal and chemical methods. In biochemical processes, we use biological methods like we use microbes, methanogens to basically work on those biomass to generate the biogas, and similarly ethanol and biodiesel. So biodiesel, so if you see, we have thermochemical conversion, we have biochemical conversion, and then we have physicochemical extraction. Okay, that is one of the form of extracting oil from biodiesel from biomass. Okay, so you must have heard about these jatropha seeds. So these jatropha seeds are nothing but they are actually crushed, and whatever oil in them is actually taken out. Then it undergoes some upgradation process before being mixed with diesel or being used as a separate fuel in cars. So basically combustion represents the burning of the biomass is in an oxygen, in the presence of oxygen. So basically when combustion occurs, it's kind of chemical phenomena in which biomass is combined with oxygen to form CO2 and H2O as a major product, and there are some byproducts also that are not so much important, but they consume a lot of energy, and similarly can affect the process also. Like we have nitrogen production that acts as thermal energy carrier. So these things are there. Gasification, combustion basically is used as a phenomena in incinerators and boilers to produce steam, and then the steam turbine can be driven by these biomass and then produce power. And also a new concept called not I won't say it new concept, but basically more and more incineration based power plants are now moving towards combined heat and power. So whatever electricity can be produced from the steam is harnessed, and then whatever heat is left is then recovered in heat recovery and steam generation system. So to produce actually to produce more power, or those heat can be utilized for process heating. And in Western Europe, this phenomena is quite common. Basically, they use it for district heating. So district heating is basically providing heat to the houses so that they can use it to heat their houses and protect them from cold. So that is also a requirement because temperature is very down there in winter. Yeah. If you see gasification, so gasification is basically a kind of partial oxidation, you can say, basically to convert the biomass into syngas or producer gas. So there is a difference between syngas and producer gas. When you most people use this term interchangeably, syngas and producer gas, but no, syngas is basically CO plus H2, that is a mixture of carbon and hydrogen dioxide, but producer gas basically contains some other quantity of gases also mixed in it. So the gasification can be used to produce producer gas. So that has various usage, like in kitchen we can use it on a stove, and in automobiles as fuel, or maybe we can use it to produce some other chemicals also. Then we have pyrolysis. Basically pyrolysis liquefaction is kind of same thing, but yeah, liquefaction we have a high just a minute. So, guys, you can have a look at this thermochemical and biochemical conversion diagram. So, this is basically quite a comprehensive diagram of using biomass as energy source and different technology that can be utilized to generate various products in the form of steam, heat, power, and gaseous fuels, also liquid fuels. So, please have a look, and if there are any questions, please raise your questions in the chat box. So, let me put the slides here so that you can see. So basically, it's a very easy diagram in which different processes combining of biomass, how to utilize the biomass or to convert it into different forms of energy is basically provided. So that's okay. And be sure that many questions can be asked in the exam on this diagram. So you should have a good look at it, like how these things are actually working on, like thermochemical, which routes are there, biochemical, which routes are there. Okay. So yeah. Then moving to the next part, that is urban waste to energy conversion. So waste to energy, basically we are utilizing whatever waste is generated. So waste is something that is discarded, that has the material has already been used and it has been discarded that with no further usage. So that is waste. So what we are thinking, or what is a new concept, that it's not a new concept, but yeah, what is being proposed, that these waste does have a good amount of calorific value. It can be used as a resource to basically extract some energy. So these waste are basically first went through some recycling thing, in which the recyclables are basically metals, glass, and different type of plastics are basically taken out, that can be recycled. Okay, and whatever is left is basically refuse derived fuel. So it is basically packed, made into pellets, and then move into incinerator, that is basically energy from waste facility, a kind of thermochemical conversion. So these waste can be anything. If it does have a good amount of moisture, like in case of food waste, so we generally go for biochemical conversion, that is anaerobic digestion. But if we have a kind of like calorific value to attach to it, it's dry, so that can be used in itself in the incinerator for extracting fuels, heat, electricity, everything. So incineration is basically done by combusting organic waste. So here organic waste, basically organic means waste having carbon content in it is basically organic. So that doesn't mean, so there's a term called organic fraction of waste. So that doesn't mean it does have plastic in it. Okay, so organic fraction basically goes to food waste. Sewage sludge is loaded in airtight tanks called anaerobic digesters. Here it is kept at 35 degrees Celsius, mixed with bacteria to break it down. And as the bacteria digest the sewage, methane is basically produced. So methanogens are there that work on the sewage. There is a whole lot process there, like hydrolysis, acetogenesis, and then uh, methanogenesis, like methane production. And there is whatever is converted to methane is basically biogas is formed, a kind of gas which has a major components as methane and CO2, and whatever is left out is basically a mixture of the material and water, that is a slurry or kind of digestate. Okay, so that has a good fertilizer application, because the NPK values are good in that digestate. The methane can be used for different various purposes, like we see in case of natural gas utilization. So natural gas is basically methane, 95 to 98% methane. Okay. So first thing about this, uh, the different routes of biomass conversion, we will talk about this biochemical conversion. So if you see the biochemical conversion, it basically entails breaking down biomass into carbohydrates available for processing into sugars, and which can then be converted into biofuels, bioproducts through the use of microorganism and catalyst. Okay, that is very much important. So, and then we can, it can also be led to production of ethanol, like through fermentation. So ethanol, we are basically looking into different application of this ethanol, basically in the automobile application, and then this ethanol can be blended with petrol also. So these things are very much going into a fast pace, and in upcoming decades we may see quite a good amount of blending of ethanol into the petrol, and can be utilized in the cars. Okay. So ethanol basically produced by action of microorganism on the carbohydrates. Carbohydrates can be divided into three major class, basically monosaccharides, oligosaccharides and polysaccharides. Oligosaccharides basically something which has very simple hydrocarbon which cannot be hydrolyzed into simpler compound because they are already simple like glucose and fructose. Oligosaccharides basically yield few but defined number of monosaccharide molecules on hydrolysis like sucrose and maltose. So when you go for uh, hydrolysis, so these can be converted to glucose, fructose similarly. Polysaccharides are higher molecular mass carbohydrates yield a large number of monosaccharides. Okay, so starch and cellulose can be one of the example of polysaccharides. And ethanol fermentation involves biological conversion of sugar into ethanol and CO2. So this is the fermentation reaction. So yeah, this reaction is very much important when you are going to look into the different uh, um, like way of production of ethanol from biomass. Okay, biochemical conversion of biomass. So one of major applications, biodiesel. So biodiesel is a more complex fuel than bioethanol. Bioethanol is kind of simpler type of fuel because fuel sugar is fermented and then bioethanol is produced. Ethanol like C2H5OH is produced. But biodiesel is not like a C2H5OH. It does have a range of hydrocarbons. So it can have a range of like hydrocarbon compounds containing C14 and can go up to C22 also. And so basically, it is basically a mixture of esters of fatty acid that differed in various chain length and unsaturation level also. And the most suitable triglyceride feedstock for biodiesel production should have a chain length like very high chain length. And basically to convert biomass to biodiesel basically requires or oil biomass oil to biodiesel is basically transesterification is the name of reaction that goes into it. Okay, and so I'm sure till this slide you have got a good idea about this biochemical conversion of biomass. Now we will move towards thermochemical conversion, and then we will be looking into this anaerobic digester as a whole. Like it is quite a good topic and does contain a good amount of knowledge about how these organic fraction of waste can be converted directly to biogas using this anaerobic digester technology. So we'll look into that in upcoming slides. So thermochemical conversion of biomass basically involve biomass structure degradation with oxygenic and anoxygenic atmosphere. So when you are saying oxygenic, then you are going for gasification and incineration, and anoxygenic is basically anaerobic, like we don't have any oxygen so at high temperature. Okay, so it includes three kind of technology, that is gasification, pyrolysis and direct liquefaction. Okay, so this is the setup for pyrolysis of biomass. Pyrolysis basically involves the conversion of biomass into fuel with at inert condition with some heating rate and some temperature range is there. So we have some particle size also that does influence the products. So heat, biomass and inert gas, these are some of the input to pyrolysis, and the output is basically biochar, syngas and bio-oil. So yeah, bio-oil can look like, it doesn't look like such dense or viscous, but it can be dense and viscous also. So there are different, depending on how you are performing the pyrolysis, we can obtain different type of products. Okay, product of pyrolysis process. So these biochar can, one of the application of biochar can be like it does have a carbon, so it can be activated to produce activated carbon. Another application can be these biochars can be applied as a soil conditioner in soil. Okay, so these are one of the application. And another biochemical conversion route is gasification process. So this gasification is quite like basically we are not performing gasification in inert atmosphere, okay, we are basically using kind of partial oxidation. So some, if biomass has some carbon, hydrogen, nitrogen, CHNSO, like elemental content in it, so we can derive a formula like CHNSO formula. So that can basically, then based on that formula we can have a stoichiometric ratio, deciding stoichiometric ratio of incineration or combustion. And then when you provide fuel less than that stoichiometric ratio, that basically goes into this conversion of uh, these biomass directly into producer gas. It kind of gas that is flammable. Why flammable? Because it does have a CO that goes into CO plus that combines with oxygen to form CO2, and similarly release some energy, and hydrogen is there. So hydrogen itself is a very good fuel. So syngas is one of the byproduct of the one of the major product of the process, and the byproduct of gasifiers is char and tar. So basically the char itself is actually obtained when all the process all the condition is fulfilled and all the process has been completed. The tar is basically a kind of complex mixture of higher hydrocarbon compounds that basically form a kind of viscous brown liquid. So there is no single definition of char that can be applied to a product, but yeah, tar is basically a kind of viscous brown liquid that does have a good amount of like higher carbon chains, hydrocarbons in it. Okay. Now after gasification, we have this aerobic and anaerobic decomposition. So aerobic decomposition, basically bacteria decomposes biomass to produce CO2 and ammonia. Okay. So aerobic decomposition, then we have total carbon component completely gets oxidized to produce CO2, and because we are getting CO2, so no, like in case of pyrolysis gasification we are getting oil and gas, but here we are not getting any fuel. So yeah, that conversion into CO2 is there in aerobic decomposition. In anaerobic decomposition, biogas is produced from wet biomass with about 90 to 95% water content by the action of anaerobic bacteria. So basically what we do, we make a slurry, and that slurry goes into digester, and basically these bacteria work on those slurry, then they break down those molecules, and then some reaction occurs and methane is generated. Part of carbon is oxidized and another part is reduced to produce CO2 and CH4. So similar happens, and these bacteria live and grow without oxygen. So this is one of the requirement of anaerobic and decomposition. It doesn't not only oxygen, it does have a specific range in which it works actually in converting those carbon into CO2 and CH4. So basically there are some range like temperature zones are there, mesophilic zone, thermophilic zone is there, and we have C by N ratio that doesn't it should not go beyond 30 to 1. Similarly temperature range, C by N ratio, moisture content should be 60 to 80%. So these are some of the criteria that has to be fulfilled when you are going for anaerobic decomposition or aerobic decomposition. Similar criteria exist there for thermochemical conversion also. So like if you are going for thermochemical conversion, it should have a moisture content less than 35% as per the Municipal Solid Waste Management Manual in India. But yeah, if you are going for higher quality RDF1 type of components or waste, so yeah, you have to go for less than 10% of moisture. Biogas technology. So biogas technology is biogas technology is basically we that I was talking about is anaerobic digestion. So anaerobic digestion is basically done in a kind of digestive chamber, so called digesters. And then the digester have some inlet feed tank and then outlet tanks, and that works basically as storage of digestate and the slurry, input slurry. Okay. Uh, One of the key requirements of this digestive chambers are basically they should work into a typical temperature zones. So these temperatures has to be maintained throughout the digester period, the period of operation of the digester. So it is basically a thermophilic zone when you are going for 50 to 60 degrees Celsius, and mesophilic zone when you are going for 30 to 40 degrees Celsius. So both the zones of operation does have kind of pros and cons attached with them, but generally what we see in research papers or scientific community is more looking into mesophilic zone because the temperature is low here and those temperatures can easily be achieved and maintained. So this is one of the major requirements. It has to be sustained. So yeah, that is why, and also there is some clear cut advantages over thermophilic zone when you are going for mesophilic zone. So we have feedstock as cattle dung, vegetable waste, co-digestion, additives, orange peel, newspaper, and tea waste. And basically, whatever biogas is generated, so these biogas basically go for purification. So what does happen in purification? We strip out the biogas of the CO2, then it is kind of rich in methane. So basically, CO2 doesn't add any value in terms of calorific value. It doesn't add to the calorific content of the biogas. So yeah, and then combustible mixture of CH4 and CO2 is best biogas produced through decomposition. Composition gases depend on the feedstock. So yeah, if there is a feedstock which is rich in carbon, then you will get CO2 and CH4 as the major products. But if there is a feedstock which has some nitrogen content in it, so you can expect some of the nitrogen can get transferred to produce like H2S gas is there, which is produced depending on the presence of hydrogen and sulfur in the input feed. Another important concept is HRT. HRT is basically hydraulic retention time. It is kind of like how much for what duration these slurry that you are feeding to the biodigester remains in the digester for the microbial activity to occur and the biogas to be produced. So that is hydraulic retention time, that is HRT. So if you see the anaerobic digestion process, it does consist of four steps. So in first step, you have this. The process consists of four steps. So if you see process flow, it does have a lot of steps. Like the first step is basically when you input the feed to a shredder. So shredder is there, which basically reduce the size of the component to a very small size, like less than 2 mm. Okay, then these organic feed is then taken to this slurry preparation chamber where water is mixed and a specific TS ratio is maintained, and that at that TS ratio the slurry actually goes into this biodigester, and in biodigester it does remain there for a specific period of time depending on the type of feedstock. Okay, and after remaining in the specific period of time biogas is produced, and whatever is left, which is basically leftover digestive slurry, is actually uh, transferred to some storage chambers, digestate storage chamber, and can be used as a fertilizer in the fields. So this is one of the advantages. And whatever biogas is basically produced, first the upgradement occurs of that biogas. Second is basically it is stored by compressing it in a cylinder. Okay, so it is not like biogas is being produced and then you are going to store it, because the rate of generation of biogas can vary depending on the microbial activity, but we need a constant flow of biogas and with a specific pressure to burn it. So that is why we store it in a vessel, and then that can be utilized for burning in the kitchen and other application. Uh, we have now going now if you see the process, what processes are happening inside the anaerobic digester. So first process is basically hydrolysis. It is basically breaking down of those proteins, lipids, and carbohydrate into smaller molecules like amino acids, sugars are there. And we have acidogenesis, that is kind of a fermentation type of process where fatty acids are generated, like VFA, volatile fatty acids are generated. Then we have acetogenesis, where acetates and hydrogen are generated. Okay. Then after acetogenesis, now comes the role of methanogens, like methanogenesis. These methanogens work on those acetates and hydrogen to release CH4 and CO2 as the major constituent of biogas. Okay. So if we see, these are some of the chemical reaction that actually occurs in a biogas plant to produce kind of methane and CO2. So it does mean like a kind of series of steps occur to produce methane. Another thing is that the energy efficiency of conversion of this carbohydrate to methane is basically, if you see, like one of the important carbohydrate molecule is glucose. So glucose has a molecular weight of 160, 180 something, and then it does have a calorific value of 16 megajoule per kg. And molecular weight and heat of combustion of methane, if you see the major product of biogas digester, like anaerobic digester, is methane. And methane basically does have a very low molecular weight, like one carbon and four hydrogen, that makes it 16. And whatever is there, this 55 megajoule per kg can be basically utilized for burning it in a gas stove to produce heat, and it can also be used in a engine to produce power. Okay. Okay. So factors affecting biogas yield is basically C by N ratio. It should be optimum, varies between 25 to 30 to 1. Then temperature is basically psychrophilic zone is 25 degrees Celsius, mesophilic is 35 to 40, and then we have thermophilic range 50 to 65. pH values should be between 6.25 to 7.50. Loading rate, basically amount of waste material fed per unit volume of waste capacity. Hydraulic retention time is average period that a given quantity of input water remains in the digester to be acted upon by methanogens. Then we have toxicity that inhibits the growth of pathogens. And we have dilution and consistency of input, like uh, TS percent is 8% and VS is 75% of the TS content. Okay. Then we have some other factors like effect of agitation, like stirring. Okay. And then we have effect of additives also, like different metal powders are added in the digester to boost the biogas generation. So let us solve one numerical here related to the biogas production and volume, deciding the volume of digester. So basically, let me give you some time to solve this numerical so that we can go. Okay, so let's take some 5 minutes to solve this numerical, and try to solve this numerical. And if you won't be able to solve this, then I will try to solve it for you guys. Okay. Okay, so did you solve this question? Let me check the answers if anyone of you, oh, sorry, has got the answers. Okay, so let me check if any one of you has got the answers. So let me solve this question for you guys actually. So basically, this is quite easy question. You just have to understand how to approach these type of questions, these type of numericals. Okay, so first thing is that key engine generator system running on biogas is proposed to be installed at Arunachal Pradesh to produce 2 kilowatt of electric power. So here you need to get 2 kilowatt. Okay, and then estimate the volume of digester. So you need to estimate the volume of digester. So CV of biogas is given. Okay, efficiency of generator is given, and then energy efficiency is also given. HRT is also given. Okay, so basically here you want to calculate the powers. First thing which you do is power input to engine. You need to calculate the power input to engine. So basically efficiency of these two are given. So you need to get it here, power input to engine. So basically you will divide the 2 kilowatt by the efficiency of generator, that is 90%, and then efficiency of engine, that is 30%. So power input to engine is 7.4 kilowatt. Okay. And then to produce 7.4 kilowatt you need to input some quantity of biogas. So this is the formula. So with this you will get the MF, like you know the CV, you know the P, you will get the mass of biogas required. So you will get the mass of biogas required. That basically means 39.1 31.96 kg per day is basically required, and mass of fresh cow dung is basically 31.96 upon 0.08. Okay, so this 0.08 is basically density of the this cow dung. Okay, then we have 399, not density, sorry, 8% is the TS content of the biodigester plant. So okay, so 399.6 kg per day is basically required. So volume of fresh cow dung, you multiply it with the density, that is 0.9. So this much is the volume. So equal volume of water should be added, okay, to get the slurry. Okay, the volume of slurry will be this much, and then HRT is 40 days. So volume of digester will be 709.2 into 40. It is 28768 liter. And that basically means 29 meter cube volume will be required for the digester. Okay. So see, these questions are quite maybe calculative. Maybe you can say kind of conceptuals, but yeah, when you draw this, so first thing which you do is to draw this block diagram. So you have a biogas plant, that is an anaerobic digester, then you have engine, then you have generator, and then you have electric power. So if you draw this block diagram, most of the question, and then put the values, write the values at different locations, whatever values you know, then you can easily solve these type of questions if you know the process how to approach these type of questions. Okay. Okay, so if there is any question which you want to ask here. Okay, so let's move to the next part of the question. Okay, so let's move to the quiz question then. These are some of the things which I wanted to discuss, but I think the lecture is actually going more into details and specifics to explain the concept. So yeah, we can look back again after solving the quiz question, because these quiz question is actually designed in such a way that it will give you a more understanding of the concepts. Okay. So this was the question which I think we solved here. So I think we can skip this. This is actually 7.4 is the correct answer. So how did you got this 7.4? 2 divided by 0.9 is the generator efficiency, and then you multiply it with 0.3, that is engine efficiency. Okay. Now quantity of biomass required, so you can also calculate it. That basically that is 32. And then we have volume of diester, that was something 29 or something. So yeah, this is the correct answer. Which of the following reactions represent the water gas safety reaction? So this is one of the major reaction of the biomass gasifier. So it does what it does. It basically converts the CO2 into CO. Okay, so the CO2 reacts with H2O, that is steam or water, and then it is kind of endothermic. So some energy is required, and then CO2 is basically converted to CO, and H2O is basically converted to H2. So this kind of producing a syngas with CO2 and H2, a mixture of CO2 and H2O. So yeah, this is one of the very important reaction when you are talking about biomass gasification or biomass gasifiers. Okay. So sorry. This is the correct answer. CO plus H2O and CO2 plus H2, basically producing hydrogen and heat. So 1 mole of gaseous hydrocarbon on composition gives 4 mole of CO2, 5 mole of H2O at STP. The hydrocarbon is. So let's say hydrocarbon is CXHY. You don't know the name of the hydrocarbon, and it will just react with air, and what it will produce? It will produce CO2 and H2O. Now, just have you are saying like it will produce 4 moles of CO2 and 5 moles of H2O. So you can have a carbon balance here. So CXHY, that is X mole, equal to 4 moles. So basically X equal to 4. So C4. Then you have a hydrogen balance Y equals to 5 into 2, 10 moles. Okay. So C4H10 is the compound. You got my point? How did we obtain this C4H10? The optimum temperature for in mesophilic zone is basically 35 to 40 degrees Celsius is the optimum temperature range in the mesophilic zone, and for thermophilic it's 55 to 60. Okay. Which of the following best indicates the steps inside an anaerobic digester? So first step, I was explaining the concept of anaerobic digester. So there are four various steps. Like first step is hydrolysis, that is breaking of proteins, carbohydrate into simpler monosaccharides. Okay. Uh, that is, then we have acidogenesis, like production of volatile fatty acids are there, like fatty acid production is there. Then after acidogenesis, we have acetogenesis, that is basically production of CO2, acetic acid is there. Then methanogens work on them and then they produce CH4. So methanogenesis. So correct answer is answer C. Optimum seed by N ratio for maximum biogas production. So it does vary between 25 to 30. So you can take 30 to 1 as it is present in the answer. This is kind of very very important question. Like it does have two questions and two questions are from here. So I think we should try this question. So please have a look at this question. Let me see if there is any question from you guys. I don't know why it is getting uh, Okay, so not sure why it is getting. I did. So till that time, you can actually keep solving that numerical. So if there is anything which you want to ask and which is not understood through that numerical, please have a look and try to solve it. So the way and way I explained, you make a block diagram, put the values, whatever values are available, then you will get to know which formula will be needed and which which process condition is basically will be utilized to solve those numericals. Try to solve this. This is quite easy. Doesn't seem too hard. You can easily solve these type of numericals, I'm sure. Okay, so are you able to solve this question? So does it feel very difficult to solve? So it's a very simple question. You just have to first determine the load that is needed for 6 hour family. So it does say lighting is required for 4 hours with 6 lamps. So you have 6 into 4, that is 6 lamp, 4 hours of operation. And how much it does consume? 0.126 of biogas for L. Okay. So for L, you know. Okay. Similarly, used as a feedstock, consider digestive, bio is required for cooking. So cooking is also so per person per day. So how many person are there? 6 person, family of 6 member, 0.227. Then after this, you can actually determine the total gas requirement. Basically, is the sum of these two. And after total gas requirement, let's say we have n number of cows, and then these each cows basically produce n kg per day of cow dung. Okay, so cow yield is basically 10 kg. Okay, so we have n number of cows and 10 kg per day is the yield. So basically, you can say a kind of collectible cow dung is basically 70%. Like you cannot collect all those cow dung. Okay, some of them are lost due to urine or something, and maybe some of them kind of goes into dirt or something. Okay, and weight of dry mass solid is basically, so whatever value is not given you can easily assume in it. So weight of dry mass solid is basically assume it to be 18% of the total. Okay, so 18.8 into 7 into n is basically how much is the dry solid in the cow dung. So gas production per day is basically just give me a So if there is anything which you want to ask, so please, you can easily solve this question. Try to just analyze whatever is being asked. So first, you need to get the volume of biogas that is required. Second is basically you know the amount of dry solids from cow dung, and then gas production per day. You know because gas production per yield of dry matter is given, so you can multiply it to get the gas production. So that should be equated to the biogas required. So you can get the number of cows, and basically then number of cows you get, so you can easily get the digested mass of slurry. You need to add number of cows plus 70, like if it says 77 into 10 70 kg, so 70 should be water should be added. So 70 plus 70 140 is there. And if you want 50 days of retention time, so multiply that with retention time, and then about 90% of volume is occupied by slurry, and then required volume of digester is basically, that is 6.35 by 90%. So were you able to solve this question? Basically, what you will do, you will get this. So volume, like let me solve this question for you. If you guys have issue in solving this question, so let me try this. Okay. So basically, whatever I said, so you just have to calculate the gas required for lighting. So take your calculators. This is the gas for lamp, then 4 into 6 hours. So that comes out to be around 3.024. Okay. Then for cooking purposes, it will be something around 1.362. So total gas required will be 4.386. Okay. So this is the amount of gas that is required. Then we have let n number of cows is there. So each cow will produce 10 kg per day. So 10 n will be the amount of like slurry which you are getting. And then after 10, like 70% of that is being collected. So for 10 n amount of slurry cow dung that is being produced, you get 70%, that is 7n. And then for 7n you get gas production of around 0.34 meter cube per kg, that is 0.34 into 7n is basically the amount that is required as a biogas. So this has to be equated. हाँ एक मिनट. हाँ yes sir. Okay. Okay. So after equating these two, like amount of biogas required with the amount of biogas that is basically produced. So you will get the N, that is number of cows. So that comes out to be around 10.24. So you can assume it to be 11 or 10, whatever you want. Okay. So daily feeding, 70 like 0.7% is collected. So 70 is the daily feeding. Then you will put a similar amount of water into that to make it a curry. So one slurry. So 140 is the amount of slurry that will be produced, and the density is basically given. So you will get it into meter cube basically. So for meter cube and for 50 days of retention time, that is basically given, or you can assume it as a retention time because it will take similar about for cow dung, the retention time is generally around 50 days. So we'll get the volume of digester. Okay. And basically the above 10% is be kept empty so that whatever gas is formed is collected. So it can vary from 10 to 20%. So depending on that, you can take the values. So volume of digester plant will be something around 7, okay, 7 meter cube, and then number of cows is basically 10, and then okay. So this is one of the question that you may feel very lengthy or something which is difficult to solve, but it is not that difficult. If you have a good approach, you can easily solve that question. And this is the last question. I want you guys to take it as assignment and solve it whenever you find time. And then if you didn't get the answer, I will discuss it in the next class. So, okay, thank you guys. Thank you for attending this live interaction session. And I hope it was a very great interaction session. And we'll again meet you again on next Tuesday from 7 to 9. Thank you.